What happens when a single fighter jet faces impossible odds deep in enemy territory? Picture this: a Ukrainian pilot flying a Soviet-era MiG-29, carrying French precision bombs, navigating with nothing but a paper map taped to his knee, while Russian radar systems hunt him through hostile airspace. This is the story of one of the most harrowing precision strike missions of the modern conflict, where everything that could go wrong did go wrong. It was 2:47 in the afternoon when our story begins. A lone Ukrainian MiG-29 Fulcrum had just crossed into Russian airspace, its twin engines screaming as it hugged the treetops at dangerously low altitude. The pilot knew he had exactly 12 minutes of fuel reserves to complete what military strategists would classify as a near-suicide mission. His target, a seemingly untouchable Russian border guard post that had been funneling critical supplies to enemy positions for months. But fate had other plans. As the fighter jet raced through the forest canopy at over 180 kilometers per hour, disaster struck without warning. A crow, simply going about its daily business, collided with the aircraft's left engine intake at the worst possible moment. The impact was devastating. Those massive compressor blades, spinning at 13,000 revolutions per minute, turned the unfortunate bird into a deadly projectile that immediately caused catastrophic engine damage. The sound was unmistakable, that grinding, mechanical shriek that every pilot dreads. A compressor stall. The MiG-29 suddenly lurched violently to the left, its nose dropping toward the dense forest below as the asymmetric thrust tried to tear the aircraft apart. In that split second, years of intensive training kicked in for the Ukrainian pilot. Right rudder to compensate for the uneven engine power, left hand pulling back desperately on the control stick to arrest the terrifying descent, right hand frantically hitting the engine restart procedures. The altimeter was unwinding at an alarming rate. 200 meters became 180, then 160. The tops of pine trees flashed past the cockpit canopy, so close that individual branches were clearly visible. The pilot had maybe 10 seconds before impact, but the engine restart sequence required 30. It was a mathematical impossibility that would define the next few minutes of this incredible mission. Meanwhile, just kilometers away, a Russian radar operator was having what he thought would be a routine afternoon. The podlet radar system, specifically designed to detect low-flying aircraft and cruise missiles, had been picking up intermittent contacts for the past few minutes. Small radar returns appearing over ridgelines, disappearing into valleys, behaving exactly like migrating birds or atmospheric anomalies. The operator had achieved a brief lock on something, lasting just 6 precious seconds. 2 more seconds and he would have had a complete firing solution, but the contact vanished behind terrain features once again. Faced with a choice between filing extensive paperwork for what was probably another false alarm, or simply letting the next shift deal with it, the Russian operator made a decision that would prove catastrophic for his side. He chose coffee over duty, walking away from his console just as the damaged MiG managed to coax its left engine back to life at barely 140 meters altitude. The Ukrainian pilot felt the blessed sensation of balanced thrust returning as both turbine engines synchronized their power output. But the damage was severe and irreversible. The engine was running rough, its compressor efficiency reduced to just 30% of normal operation. Worse still, the near crash had consumed precious time and fuel reserves. Those 12 minutes of operational margin had shrunk to just 3. Every second now counted in ways the pilot could barely comprehend. Then came the power lines. These massive transmission cables weren't marked on any of the tactical maps the pilot was using. They appeared in his windscreen like an invisible wall, suspended 60 meters above the valley floor and stretching as far as the eye could see. At 650 kilometers per hour, he had exactly 2 seconds to react or die. The pilot yanked back on the controls with tremendous force, pulling 5 times the force of gravity as he fought to maintain consciousness while the MiG rocketed skyward. The electromagnetic field from those high-voltage cables made every instrument in the cockpit dance wildly, adding another layer of chaos to an already impossible situation. But the pilot cleared the obstruction by less than 10 meters, his aircraft shuddering from the electromagnetic interference as he pressed onward toward his target. Behind him, the replacement radar operator was puzzling over strange electronic signatures in the system logs, wondering what could have caused such unusual returns just minutes before his shift began. By the time anyone figured out what had really happened, it would be far too late. The navigation checkpoint appeared exactly where the paper map indicated it should be, a distinctive bend in the Desna River that confirmed the pilot's position with analog precision. 10 kilometers to the release point, flying on one damaged engine with fuel for exactly one attack attempt. What came next would test every limit of both man and machine in ways that seem almost impossible to believe. The pilot began what military aviation experts call a suicide climb, a vertical ascent through 8,000 feet of heavily defended airspace where concealment was impossible and detection meant certain death. As the throttles pushed forward and the control stick pulled back, the G-forces hit like a sledgehammer. 6 times the force of Earth's gravity crushed the pilot into his ejection seat, while his specialized G-suit inflated desperately, squeezing his legs and abdomen to prevent blood from draining away from his brain. But even with this life-saving equipment, the human body has limits. At 3,000 meters altitude, his vision began graying at the edges. At 5,000 meters, it narrowed to a tunnel. At 6,500 meters, consciousness nearly slipped away entirely, his hand locked on the control stick purely by muscle memory and years of training. The MiG's nose pointed almost vertical now, both engines screaming at maximum thrust, while the damaged left power plant vibrated so badly it threatened to tear itself from its mounts. The pilot couldn't reduce power. He needed every meter of altitude he could possibly achieve, because he had just announced his presence to every air defense system within a 200-kilometer radius. Then the weapons interface crashed. The French-designed precision bombs were connected to the Soviet-era fighter through an improvised interface that Ukrainian technicians had cobbled together in a warehouse. It worked perfectly on the ground during testing, but at 6 Gs and 7,000 meters altitude, the voltage regulator failed catastrophically. The weapons control panel displayed error messages in French, a language the pilot didn't speak, while the bombs remained electronically silent, unaware they were supposed to release in just 20 seconds. This was the moment when everything should have ended in failure. Instead, it became the moment that defined the entire mission. The pilot's oxygen-starved brain struggled with emergency procedures, while his left hand maintained the climb and his right hand frantically worked through backup systems. Manual override switches, backup power circuits, master arm cycling. Nothing seemed to work as the critical release window approached. That's when the Russian Su-35 fighter fired its missile. 72 kilometers away, the enemy pilot had been vectoring toward radar anomalies when the climbing MiG suddenly appeared on his scope like a rocket ascending toward the heavens. There was no hesitation, no attempt at identification. The Russian pilot locked up the target and fired a hypersonic missile, traveling at 6 times the speed of sound, covering the distance in just 36 seconds. The Ukrainian pilot's radar warning receiver erupted in electronic screams as the incoming missile bore down at 2 kilometers per second. But he couldn't evade, not yet. He still had to release those bombs, and time was measured in heartbeats. His left hand held the aircraft steady, while his right found the emergency release switches, individual manual controls that bypassed the failed digital interface entirely. 8,000 meters, release point. Now or never. The pilot hammered the first manual release button and felt nothing. 1 second, 2 seconds. 3 seconds. Finally, the bomb dropped, its rocket motor igniting after a heart-stopping delay that felt like an eternity. The second bomb released faster, the manual systems now warmed up and responsive. Both precision munitions fell away and immediately pitched upward, their rocket motors driving them even higher while the pilot prepared for the fight of his life. The evasion maneuver was a split S, rolling inverted and pulling toward the Earth in a descending half-loop that traded precious altitude for life-saving speed. 9 times the force of gravity crushed the pilot as his vision went completely black for 2 terrifying seconds. When sight returned, he was diving through 4,000 meters, while the hypersonic missile continued tracking his every move. His chaff dispenser fired 3 bundles of radar-reflecting strips before jamming completely. The electronic countermeasures pod, overheated from the brutal climb, hit its thermal limits and shut down automatically. With the missile now just 10 kilometers away and closing fast, the pilot had one desperate option left: the notch maneuver. By turning perpendicular to the missile's flight path, he created a situation where the relative motion went to 0. The missile's seeker, programmed to ignore stationary objects to avoid being fooled by ground clutter, broke its lock and flew past just 100 meters behind the MiG. Fragments from its self-destruct mechanism peppered the fighter's tail, punching small holes in the rudder, but the pilot was already diving for the Earth, trying to get back to the safety of low altitude where radar coverage was limited. Behind him, 2 French precision bombs were climbing toward their apex, one with a rocket motor that was already beginning to sputter from contaminated fuel. Everything now depended on systems and technologies that had never been tested under these exact conditions in a combat environment where the margin for error was measured in meters rather than kilometers. The bombs reached their maximum altitude of 8,500 meters, their rocket motors spent, and beginning their long fall toward the border guard post at Belaya Berezovka. 4 minutes of flight time through empty sky, guided by satellites they couldn't communicate with, and seeking targets with infrared sensors that couldn't yet see their destination. In combat, military experts know that things almost never go according to plan, and this mission would prove that rule in spectacular fashion. The first bomb's rocket motor had ingested contaminated fuel, water vapor that had condensed in Ukrainian fuel trucks, frozen at high altitude, then turned to steam in the combustion chamber. Instead of full thrust, it produced only 60% power for 20% less time than programmed. The bomb's onboard computer, a French-designed system no bigger than a wallet, calculated that the current trajectory would impact 2 full kilometers short of the intended target. But that was just the beginning of their problems. The Krasika electronic warfare vehicle near Bryansk activated at maximum power, flooding GPS frequencies with precisely tuned interference. The signal from navigation satellites 20,000 kilometers above, transmitting at tiny fractions of a watt, vanished instantly. Both bombs lost satellite navigation simultaneously and switched to inertial guidance, mechanical gyroscopes spinning in the dark, accumulating 2 meters of navigational error for every second of flight. By the time they reached their target area, they would be nearly 500 meters off course. For conventional weapons, this would mean complete mission failure. But these were not conventional weapons, and they had backup systems that would prove absolutely crucial in the next few minutes. The bombs switched seamlessly to their secondary guidance mode: inertial navigation for general direction, infrared sensors for terminal targeting. But now they faced a new enemy: the sun itself. At 1449, the sun sat directly in the flight path of the descending munitions, its infrared signature overwhelming every sensor designed to distinguish ground targets from background heat. The second bomb's infrared seeker activated at 3,000 meters and immediately locked onto a heat source of nearly 6,000 degrees Kelvin. The computer recognized this as clearly not a ground target, breaking lock and searching again, finding nothing but white-hot solar glare. For 15 seconds, covering 4 full kilometers of flight, the bomb flew essentially blind while navigation errors accumulated and trajectory degraded. Meanwhile, the first bomb encountered wind shear at 5,000 meters, the edge of the jet stream, an 80-knot river of air moving west to east. The powerful winds caught the bomb's control fins like a sail, yawing the entire weapon 20 degrees off course in less than a second. Its simple analog gyroscopes, never designed for such forces, tumbled completely. The bomb began spinning slowly, its fins deflected to maximum, trying to recover stable flight. The mathematics were brutal and unforgiving. Spinning at 2 revolutions per minute, falling at 280 meters per second, with impact in just 45 seconds, the bomb's tiny processor had to solve complex differential equations in real time. It needed to calculate fin positions that would stop the spin without inducing an even worse instability, all while dealing with damaged gyroscopes and accumulated navigation errors. Then the Russian S-400 air defense battery at Klimovo detected them. 2 small contacts falling eastward with radar signatures of 0.2 square meters. The operator wasn't entirely sure what he was looking at. Too small for aircraft, too fast for helicopters, wrong trajectory for ballistic missiles. But standing orders were absolutely clear. When in doubt, engage the threat. 2 massive surface-to-air missiles roared from their launchers, accelerating toward the bombs with devastating intent. But it was a futile gesture, born of desperation rather than tactical wisdom. The missiles were designed to intercept aircraft with predictable flight paths, not bombs in ballistic freefall whose trajectory was determined purely by gravity and atmospheric drag. The S-400's targeting computer couldn't calculate a proper intercept solution, and the missiles flew past harmlessly, their seekers finding nothing but empty sky. At 2,000 meters altitude, salvation finally arrived for the first bomb. Its uncontrolled spin had actually carried it east of the intended flight path, away from the blinding sun. The infrared seeker, finally clear of solar interference, activated and immediately found what it was looking for. 3 BTR armored vehicles, parked in formation with engines running hot. Lock achieved with textbook precision. The second bomb took a different approach to the solar interference problem. Instead of relying purely on heat signatures, it began searching for contrast patterns and geometric shapes. The target building's roof created a distinctive signature, not heat, but recognizable geometry. French programmers had included this backup targeting mode after experiences in desert combat zones where targets were often the same temperature as surrounding terrain. Lock achieved at 2 kilometers altitude. Both seekers were finally tracking their targets, but the Russians had one final defensive system to deploy. The Pantsir point defense system protecting the border guard post represented Russia's most advanced short-range air defense technology, specifically designed to defeat precision-guided munitions. Its radar could track individual bullets in flight, its missiles could intercept artillery shells, and its guns could create walls of high-explosive projectiles. But there was a critical flaw in the system's design philosophy. At 8 seconds to impact, the Pantsir's radar locked onto the diving bombs and immediately encountered a problem no training scenario had ever addressed. These contacts were approaching at 87 degrees elevation, nearly straight down, falling at over 300 meters per second. The system's computer calculated intercept solutions and displayed results that seemed impossible. Target outside engagement zone. The bombs were at 900 meters altitude, but the Pantsir's missiles had a minimum engagement range of 1,200 meters. They needed 1.5 seconds after launch for their proximity fuses to arm properly, but the bombs would impact in less than 3 seconds. The mathematics were absolutely impossible, but the operator fired anyway, desperation overriding tactical logic. 4 missiles erupted from the Pantsir system in a final, desperate salvo. Their solid rocket motors accelerated them to 3 times the speed of sound almost instantly, but physics remained merciless and unforgiving. The missiles raced upward with their seekers trying to lock onto targets that were already inside their minimum effective range before the motors even finished burning. At 400 meters altitude, exactly 1.5 seconds after launch, the proximity fuses armed as designed. The bombs were already below them, falling like stones toward their targets. The missiles self-destructed harmlessly, their fragments falling like steel rain across the compound while the operator's training took over. When missiles fail, use the guns. The twin autocannons swiveled upward, each barrel capable of firing 25 rounds per minute with 30mm shells designed to shred aircraft aluminum. The operator pressed the firing trigger, and the guns roared to life, creating a cone of destruction above the compound. But even this last-ditch effort was doomed by geometry and physics. The guns hit their maximum elevation limit at 85 degrees. The bombs were approaching at 87 degrees, still just outside the engagement envelope. The operator watched helplessly as thousands of rounds passed mere meters behind the falling munitions. The slight angle difference, meaning the difference between successful interception and catastrophic failure. The first bomb's infrared seeker was trying desperately to maintain lock on the armored vehicle exhaust plumes, but damaged gyroscopes from the earlier spin meant it was offset by 12 meters from the intended impact point. At 50 meters altitude, it made final trajectory corrections with whatever control authority remained. Impact came at 14:51. The 340-kilogram bomb punched through the building's roof at over 300 meters per second. The kinetic energy alone was sufficient to collapse the structure, but then the shaped charge detonated with devastating effect. 50 kilograms of modern military explosive created a jet of superheated copper moving at 8 kilometers per second. The asymmetric impact angle meant the explosive jet cut sideways through the building instead of straight down, and the effect was actually worse than a direct hit would have been. The diagonal blast path eliminated every load-bearing wall on the north side of the structure. The building didn't simply collapse, it toppled sideways like a felled tree, creating a massive debris field. 17 seconds later, the second bomb arrived. The damaged fin had introduced a spiral approach pattern, causing the munition to corkscrew through its final 200 meters of flight. It impacted 8 meters off target at the vehicle park's corner instead of the center, but precision wasn't necessary anymore. 227 kilograms of steel and explosive hitting at over 300 meters per second doesn't need pinpoint accuracy to be devastatingly effective. The kinetic impact ruptured every fuel tank simultaneously. The 3 BTR armored vehicles didn't explode in the conventional sense. They melted. 500 liters of diesel fuel in each vehicle turned instantly to aerosol, mixing with the surrounding air in perfect combustible ratios. The shaped charge provided the ignition source for what became a fuel-air explosion, generating temperatures of 4,000 degrees Celsius for exactly 1.3 seconds. Meanwhile, the Ukrainian MiG-29 was already turning west, re-entering friendly airspace on one damaged engine with fuel tanks nearly empty. The pilot was half-conscious from the extreme G-forces he'd endured, but he was alive and the mission was complete. Behind him, the former Russian border guard post burned with intense heat, its strategic value eliminated in a matter of seconds. This mission represents everything that makes modern aerial warfare so incredibly complex and unpredictable. Equipment failures, human errors, environmental factors, and pure chance all played crucial roles in determining the outcome. The Ukrainian pilot faced impossible odds with damaged equipment, outdated maps, and fuel reserves measured in minutes rather than hours. Russian defensive systems performed exactly as designed, yet still failed to prevent mission success due to attack profiles they weren't optimized to handle. The broader strategic implications of missions like this extend far beyond the immediate tactical results. Every successful precision strike against supply routes and command posts degrades enemy operational capability in measurable ways. Border crossing points, fuel depots, ammunition storage facilities, and communication hubs all represent critical vulnerabilities in any military supply chain. Modern precision-guided munitions have revolutionized the way conflicts are fought, allowing small numbers of aircraft to achieve effects that would have required entire squadrons in previous generations. But as this mission demonstrates, even the most advanced weapon systems are ultimately dependent on human decision-making, environmental conditions, and the countless variables that define real combat operations. The integration of Western precision weapons with Soviet-era aircraft platforms presents unique technical challenges that Ukrainian forces have solved through innovative engineering and remarkable adaptability. These hybrid systems represent a fascinating glimpse into how modern militaries adapt existing equipment to meet evolving battlefield requirements. What makes this particular mission so remarkable isn't just the successful completion, despite overwhelming odds, but the cascade of failures and recoveries that defined every phase of the operation. From bird strikes to GPS jamming, from solar interference to wind shear, every possible complication seemed to occur at the worst possible moment. Yet through skill, determination, and perhaps a measure of luck, the mission achieved its strategic objectives. This is the reality of modern aerial warfare, not the sanitized version shown in movies or video games, but the messy, chaotic, unpredictable environment where split-second decisions determine life and death outcomes. It's a world where paper maps prove more reliable than GPS satellites, where analog systems outlast digital interfaces, and where human judgment remains the most critical factor in mission success or failure. The lessons learned from operations like this inform military doctrine, equipment design, and training programs for years to come. Every failure mode, every successful adaptation, every tactical innovation gets analyzed and incorporated into future operational planning. This is how military forces evolve and adapt to changing battlefield conditions. As conflicts continue to evolve with new technologies and tactics, missions like this Ukrainian precision strike will be studied by military strategists and aviation specialists worldwide. They represent the cutting edge of how modern air forces adapt to complex, multi-layered defensive environments, while achieving strategic objectives with limited resources and overwhelming constraints. The courage and skill demonstrated by pilots flying these impossible missions cannot be overstated. Operating deep in hostile territory with damaged equipment, minimal reserves, and enemy forces actively hunting them requires a level of professionalism and dedication that defines the very best of military aviation. These are the stories that remind us why freedom and security can never be taken for granted, and why the skills and sacrifice of military professionals matter more than ever in our complex modern world.